All right, so today on IoT Connecting Things, we have some circuit analysis. And what is circuit analysis? We actually have done some of the circuit analysis already. And let's go through this show and then also take a look at the Tinkercad at some point. Contents of the course. Okay, we are somewhere in the circuit analysis now. So the second week started. We are still going through the very fundamentals. Last week we had the Ohm's law, series and parallel connection of resistors, basic measurements like voltage and current, voltage across a device, and current should be put on the way of the current goes. So in between you break the connection and put the current meter in the middle. Then we talked about electric power, LEDs, how to turn on a LED, and then switch microcontroller connections, and then how to simulate things on the Tinkercad. And thank you. I noticed that I think about 99% of you have returned the first exercise. Excellent, excellent work, and on time. I will take a look at the exercises probably starting tomorrow. Today will be a full teaching day. Today we are going to go through a couple of things. So circuit analysis fundamentals, especially Kirchhoff's laws, and then using Kirchhoff's laws, and then circuit analysis shortcuts, which are practically the same as the last time. We just take a look at them from another view. More examples. And we are still working on DC signals, so basically with the resistors. Next week we go and see this AC part, but there is not much difference actually to the DC part. It's just some of the mathematical markings are changing, but that's not a biggie. Okay, the purpose of doing circuit analysis: solve all unknown parameters of a circuit, meaning all currents, all voltage drops that are shown on a circuit diagram. Okay, there's some honesty here. Only about 1% of you will ever need this in your future work as ICT engineer. So why we are actually teaching this circuit analysis? Well, most of you would benefit on understanding of how the electronic devices actually work. So we are still building your engineering fundamentals here, fundamental or foundations, where they build more stuff. So basically that's why we are teaching this. And on the other hand, when you start thinking, do you really apply any, the laws of mechanics either on your future work? Not necessarily, but it's definitely helps you to understand the how nature works, and that's one of the things that the engineers actually need to know. And okay, there are a couple of simple examples, everyday life examples here. For example, what happens when a device battery runs out of juice, how to avoid it. Okay, now we are talking about power consumption, especially the current consumption, how much current is actually taken out of the battery, like on the first exercise. How modern LED lights with dimmers operate. So actually there's a dimmer kind of the old-fashioned way is just to put a resistor there. Not a good idea, since basically then you are consuming most of the power on the resistor and not on the LED. And again, we are talking about power and power consumption and how to save energy. For example, this kind of couple of things. And yeah, so let's talk about the unknowns. So on this, solve all unknown parameters of a circuit. What are the unknowns then? Remember this one from last week? That's still a typical circuit schematic. All component values like R1, R2, R3 are considered to be known. But also, if there are some voltage sources with marking U, that's also considered as a component with a value. So U can be used as a value. So what are then the unknown parameters? In this example, they are also something that we haven't marked there yet. So currents, how much current is flowing from the flowing through each component, and then also the voltages are unknown. And those unknown parameters can be solved, and that's what circuit analysis is all about. Solving unknown currents and voltages. And why? Well, so that you would understand how electronics work. Couple of laws. Last time we had Ohm's law. Okay, that's wonderful, but we also need a couple of other laws, like Kirchhoff's current law, which is also the called as the first law of Kirchhoff. And there basically it states that the current doesn't disappear. So basically, if we have a current junction like this one here, red circle here, there's a current junction, the same, there are these conductor wires that are connected there together. So one current is coming from, or the total current is coming from the power supply, from this voltage supply there. There is a current, and then it basically splits into parts, I1 and I3. I mark those I1 and I3 so that they basically match these resistor, the titles R1, R3. That's just a easy way to keep track of which current is where. So practically what Kirchhoff's current law says that whatever comes to this current junction, which is I, is basically same as the sum of the outgoing currents. So I1 plus I3, they are the same as I. Simple, very simple. So it just says that, as I said, the current doesn't disappear from a circuit. Then we have the second law, which is the Kirchhoff's voltage law, where we actually have these closed circuit loops. Like here is one. Should I actually mark it with this one? Okay, here we have one closed loop. So practically on this closed loop here, the sum of voltage differences is 0. And we start from this point. Okay, we have one voltage drop here, another voltage drop here, and then third one here. Okay, which is negative. So, okay, there's an example on that one. So practically we have to also take into account the basically it's the default, or actually what we think is the electric field direction, and if it's opposite direction, then basically it's negative. Another way of thinking it is, okay, so we have one voltage here, voltage supply voltage, which basically is constructed from this voltage here and another one here. Practically, we also already used that law, or when we were talking about this the voltage divider. And then we have another closed loop here. And those are the laws. So practically, what if you have any, whatever complex circuit you have with resistors, energy sources, it may have also capacitors. So you basically go and you can make these equations using first law and the second law, and then using those and Ohm's law you can solve the unknowns. But okay, but those are the basic laws. Ohm's law, Kirchhoff's current law, Kirchhoff's voltage law. Let's go a little bit forward. Yes, the circuit analysis. You use those laws. So practically that's the kind of 1, 2, 3, 4. Do these, and then you have the solution. So practically you start from writing equations for each current junction using Kirchhoff's current law. Then write equations for each closed voltage loop using Kirchhoff's voltage law. And then the last equations usually use Ohm's law to make the equations for each resistor or impedance in general. And finally, you solve the equation group. Sounds quite straightforward way of doing things. And then, of course, I have an example. I hope you are not getting bored of this one single example. I just try to keep things simple enough, but not simpler than that. So writing the equations for each current junction, meaning the Kirchhoff's current law. In this case, it means that we have basically two current junctions here, this one and that one. However, we can simplify things a little bit, since practically we have this first equation, I equals I1 plus I3. So incoming current I is the same one as I1 and I3. Okay, on the other hand, this current junction is quite symmetric to that one, since now we have just these two currents coming in. So that's actually I1 plus I3 equals I2. Okay, we can simplify quite a lot here. If we have this I2 current marked, since it's a current that flows through R2, it's exactly the same as I, since the current does not disappear anymore, or it doesn't get any more current when it flows through a device. So practically this I2 is exactly the same as I, which means that these two current junctions, they give identical information. We don't need both. We need only one of the equations. Actually, adding another same equation to the equation group would not be a good idea in any case. Okay, so one equation done, which is the top one. Okay, write equations for each closed voltage loop. So that's the Kirchhoff's voltage law. Okay, that there's a small mistake here. It's not assumed current direction, but assumed the field, electric field direction. So basically, when we know that we are going from lower to higher potential, then we mark it as negative voltage. But anyways, this first voltage loop or current loop 1, this one here, we have U1. Oh, sorry, I'm missing this this U1 and U2 here. But anyways, we have U1, so the voltage across the resistor 1, and then we have U2, which is the voltage across resistor 2, and the third one is from minus to plus terminal, so it's the voltage across the U on that direction is minus U. Actually, we could have also marked, okay, we have this voltage is the same as voltage across R1 plus voltage across R2. I just mark it that way so that you can see, okay, by following exactly the Kirchhoff's voltage law things, you can actually, you practically get into the same equations. Okay, then the other voltage loop here, or current loop. So we have R3. The voltage across R3 is U3, and then we had the current flow in from up to down through U1. It means that when you are calculating the sum in loop on that direction, on clockwise direction, then you have a negative voltage here. So you have U3 minus U1 equals 0. Directly using the Kirchhoff's voltage law. However, again, it would be equally same by writing, okay, U3 equals U1. Duh. And we could actually eliminate that U3 totally using that, but just for fun, let's keep that equation also there. Okay, third part was write equations for each resistor using Ohm's law. U equals R times I, and we had those currents I1, I3, I, resistor R1, R2, R3, and then it basically they generate voltage drop on that direction, which are U1, which is equal to R1, I1, U3 is R3, I3, and then U2 is R2 times I. Those three equations. So what we got? We have 6 equations and 6 unknowns. The unknowns are there, the ones we added to the original circuit diagram. Remember, we started from this one. So that's what is given. So what we need to mark ourselves there are the currents and the voltage drops there. So basically you need to mark those on the circuit diagram yourself when you start doing the analysis. Okay, so unknowns are the ones we mark there ourselves: U1, U2, U3, I1, I3. We have 6 unknowns. We have 6 equations, simultaneous equations. So this is basically a linear equation group with 6 unknowns and 6 equations, and we then should be able to solve those unknowns, which can be a bit harsh without any tools. So I think you have been practicing this one on the linear algebra on classes on the mathematics. But okay, there are some tools to do it. I'm not sure if your math teacher has actually shown those tools yet. But I will show you at the end a little bit how to do the calculus with the proper tools. But meanwhile, we do also some engineering way. So this is old school engineering, circuit analysis shortcuts. How to solve things, say, faster. Earlier we had these basically 4 things last time. So resistors in series equals also the voltage divider, or resistors in parallel is current divider, Ohm's law, and Thevenin's theorem. So let's revisit the Thevenin's model. So sometimes it's worth of simplifying parts of the circuit by making the Thevenin's model. So practically that circuit diagram within this purple box, we can draw, we can actually make a Thevenin's model for that one, and that one actually would give you also this U out at the same time. On the other hand, you can get U out in any case, but basically if we think of this device as this circuit, so that you would add 1 resistor in this between that point and that point. So basically you would have 2 parallel resistor connections there. Then it might be actually worthwhile of thinking, okay, simplifying of things so that you have first this part, and then that additional resistor would be a load to this original circuit. By the way, this is quite close to what you would be doing on the 3rd exercise, which is theoretical circuit analysis, and also some of the Tinkercad stuff, I think. So what to do? One thing to do is solve the first open circuit voltage U2 when you think that, okay, these parameters, the circuit values are known. So we can first go and simplify the circuit using parallel resistor model. So we have R1 and R3 is certainly parallel. They are connected on both ends on the same potentials, here and there. And that actually gives you the parallel resistance. Now we know it. Okay, that was just one single formula for that one. Next part, to solve the U2, you use the voltage divider equation, which was actually the same as the series resistors. There's a series resistors of R bar and R2, and that formula came directly from the that voltage divider equation. Okay, now we have also the open the open circuit voltage there. Then in order to solve the output resistance, okay, this is a trick here. This is a nasty trick, I know. We replace the voltage source with a plain wire. And why we are doing this one? Actually, think of this U here, it's known. And we can actually also, for the analysis, we can turn it off, meaning we turn U equals to 0. Internal resistance of a voltage source is very small. So ideally it doesn't, the internal resistance is 0. It means that it can provide lots of current to any load. So if we can control the U, we can also turn it off, meaning turning the energy off, which means that we basically, for the analysis, we replace it by a plain wire. Remember, this is theoretical stuff. Never replace a voltage source by shorting it. So sparks will fly. And that's not usually good. Okay, so we can see that the R2 is parallel with R bar. Why? Okay. When you're looking at this point between A and B, this R2 is between A and B. And then when we take a look at the R bar, that's also connected in between points A and B. So, okay, so that's actually the those resistors R2 and R bar are parallel to each other when you're looking at between points A and B. So our R out, which shows up in between the points A and B, which is the same as the internal resistance, is actually that one. So now we have done the Thevenin's model for the system by those shortcuts using just the series connection of resistors as and voltage divider, current, and then the parallel resistors or the current divider. So very simple operations, and then basically our Thevenin's model for this circuit is there. VCC, that's the same as U2, equals the original voltage supply, voltage, and then there's a voltage divider R2 divided by R2 plus R bar, and the resistance of this Thevenin's model is simply that what we calculated before, which shows the R2 and parallel with that R bar. So very fast to do this Thevenin's model that way. Okay, that is one shortcut. Again, so we started from Thevenin's model, or want to do a Thevenin's model for that one. How to do it? Simplify these parallel resistors, use voltage divider equation to get the open circuit voltage, and then think that okay, that voltage supply is actually just a straight wire. For the impedance sense, it is actually exactly that. And then we have this output resistance. And we have the full Thevenin's model, like this one. All right, so then there was claimed that, okay, solving an equation group is hard. Yes, if you have only pen and paper, then it will be hard. But basically, if you have, for example, Python, then it's not that hard anymore. So practically, this equation group, we can solve it with Python, and my favorite Python version is the Anaconda distribution, which has the Python package spider there, which is the special subroutine libraries, especially for engineering and science use. And basically there you can use, for example, or in this case, we can use the symbolic Python package simply. So the keywords there are, if you want to do this kind of analysis in future, well, get the Anaconda distribution of the Python, and it comes with a spider, and then you can use the symbolic Python package simply. Okay, we have these 6 equations and 6 unknowns. Behind of that picture, there's actually a link to a video that shows it, but since I think we have time, I will show you that one on the old school way, basically. Oops. Old school. Undock that one. So basically a few things what we need to do. First, we need to import the functions that we are going to use from. Just a moment, I try to get this one a little bit bigger. By making first, I will make it smaller like that. So I'm going to solve this equation group in this symbolic package, and there I need some information. There we go. Okay, now it's also a little bit bigger. So first thing to do is we import from SymPy library everything. Okay, that's the first part, and then we actually say R1. Okay, why we are saying this one? Next, we need to introduce some symbolic variables. And symbolic variables actually are the ones we already know. So R1, R2, R3, and voltage U. Those are known, but we need to actually introduce those as symbols. So that's R1, R2, R3, U. So now those are introduced as symbols. Next, we also added some unknowns. So our unknowns are those voltages, U1, U2, U3. Those are also symbols. U1, U2, U3. And then I have I1, I2, and I. The other symbols, I1, I2, I. Okay, now we have all the symbols given. So next we need to actually type these equations there. So equations like EQ1 equals, and we introduce that one as an equation object. And then we have the first equation. Just let me show you what it was. So the first equation was the okay, blurred. Yeah, okay. You might want to actually take a look at this later on if the bandwidth is not enough currently. Sorry about that. I will actually upload these recordings as high definition. They should be available tomorrow morning as high definition videos. Sometime this tonight they will be actually on the as a normal definition on YouTube. This is because I have very low the bandwidth at my home. I'm living on countryside in between of these two villages, but unfortunately all these link towers are quite far away. Okay, and let's see. So those equations, and I cheat again. Oops, that one. Equation, first equation was I equals I plus I1 plus I3, and this is how you do it. The left-hand side equation, comma, right-hand side equation. Oops. Oh, yeah, okay. Maybe I should actually make the correct symbols first. So you saw excellent example when you mistype something, you get error messages. Better. The second equation is for the that one was the U3 minus U1 equals 0. Third equation is okay. I better take it from here actually and show you what I'm actually doing. Sorry, now it looks very small, but I'm just typing. Basically, the third equation is the same as. Oh, okay, that was the third equation. Haha, sorry. The U3 minus U1 equals 0 is the third one. The second equation was actually this U1 plus U2 minus U equals 0. That was the bigger current loop. Then equation 4, U1 equals R1 times I1. Equals. equation 5 EQ U2 comma R2 times I, and sixth equation is EQ and U3 is the same as R3 times I3. Okay, now I have the 6 equations here. Now I can actually go back to the back to that display. And here the next step is actually to solve the equation group, which is simply, I'll just give a variable solve. Here is the same as solve. Wait a minute, it looks like I'm missing from the window something here now. Better. Solve. And what we are solving, all the equations on brackets, EQ1, oops, EQ2, EQ3, E. Okay, so those equations are solved for unknowns. And the unknowns here are currents and these voltages across each component, like that. Solution took about 1 second, and then basically you can print that one in your favorite format. I usually print it on LaTeX format. I just need to take a look at how it's done. I think it's the like that one. Yes. Solve. Okay. So that's the solution. And if you want to read it in nice format, you can then you need to actually use some say mathematics editor, put it there. It will give you the answer for I1, I3, U1, U2, U3. All of them are there. Okay, so practically this circuit analysis, it's not really big science. It's really just plain old engineering. Okay, plain old engineering. And basically it starts from the unknowns. We have schematic. The things that are marked on the schematic, they are considered known. They are signal sources, voltage sources. They are actually known values, resistors, that kind of things. If we want to basically calculate how in our case, what is the Thevenin's model for that one, then we can use the circuit analysis tools for that one. And for circuit analysis, you need to know the Kirchhoff's current law, which is quite simple. You go through each current junction, check the currents, which currents are coming in, which are going out. And basically, sum of incoming currents is the same as outgoing currents. So the current doesn't disappear anywhere in between. Then the voltage law, you go through these the current loops here, or these circuit loops, clockwise or counterclockwise, and the sum on that direction is actually 0. It means that the voltage doesn't appear magically in between. it's always basically if there is some voltage source, okay, that's no magic, but within a single conductor from point A to point B, if there's nothing more than conductor, then there is no voltage drop either. So yeah, and the circuit analysis is basically comes into this very simple the rules, meaning you write the equations for each current junction, equations for each closed voltage loop, and equations for each resistor, and then solve the equation group. And in this example, things to remember, okay, if you have identical current junctions, you don't need to duplicate those. You basically can use just one current junction formula here, since practically those are the same, identical. Each closed voltage loop, you just go through the voltage drops, and things to remember, okay, if you know that you are going on the direction of assumed the electric field, higher to lower potential, then the sign is positive. But if you go against the assumed this or known electric field, then the voltage potential drop is negative. So that's why we have the negative sign here and negative sign here, since we thought that, okay, current is flowing that direction from top to bottom through R1. All right. If you make a wrong assumption on the electric field or the direction of current, it's not really a big deal. Just the sign will be opposite. As long as you follow for example, this Ohm's law, you use this one on correct direction. So Ohm's law, and then basically we have this unknowns, what we added there, and equal amount of the equations, and it can be harsh, but actually it's not. It just requires some typing of the equations, typing of the what is required to solve. And if we take a look at the Python here, that wasn't, I think that wasn't too much to do here. So first, importing this symbolic package to the Spider environment. Okay, and then say which are the symbols, and okay, be careful also here to use exactly the same symbols as you have on your formulas. That helps. I mistyped the I didn't have I2, I had I3. So basically it shows up on different place, of course. And then carefully typing these 6 equations here. If you make a typing mistake here, it'll actually also be a mistake on the result, of course. There, and then solution part, the solving this equation group is the easiest part. It's just typing solve. Which equations, what to solve. and then printing out the result. Okay, good. Or that was the another way, shortcuts. Especially the Thevenin's model is remarkably good tool for circuit analysis. You can go and simplify things a lot. And the trick on this Thevenin's model is that as long as you are working on pen and paper, you can control these parameters, and especially the voltage supply, how big voltage supply you have. You can, for the paper, you can turn it basically the energy to zero, or power to zero, meaning that it's 0 volts, which is the same as just a wire. That helps especially on this determining the output resistance. But otherwise, yeah, it wasn't that hard to do the solving the equation group, as long as you carefully type whatever you are doing there. But you are ICT. You will be ICT engineers. You should know coding, and this is just coding. And if you make a small mistake on coding, typo, then it immediately backfires. Okay, good. So, do you have any questions at this point? Okay, if you don't. Okay, if you have no questions, then let's have a 5-minute break. So we continue at say 9:59. There we go. Okay, great.